Hello and welcome to this screencast which explains how to draw splitting trees for the different types of hydrogen in a molecule to help predict line shapes of signals in the proton NMR spectrum. If a hydrogen atom or set of hydrogen atoms couple to two different neighbouring groups, then you should consider each coupling event separately. The number of different types of hydrogen depends on the symmetry or lack of symmetry in the molecule. Splitting trees can be useful for combining two or more separate coupling events in molecules and help us predict the number of lines in the signal. This is a useful aid to interpreting proton NMR spectra and assigning signals to particular sets of hydrogen atoms. In this first example, propane, you can see that there is a line of symmetry running through the centre of the molecule, so the hydrogen atoms in the two methyl groups are in the same environment as each other. This means that when we are considering splitting of the CH2 protons, we can treat all their neighbours the same, since they're all equivalent to each other. Therefore, the CH2 protons have 6 neighbours, so we'll split into 7 lines, using the n+1 rule. However, if we look at the example of 1-chloropropane, there's now no line of symmetry in this molecule, so all of the hydrogen environments are different from each other. If we consider the splitting of the CH2 protons in red, then we must consider the splittings from the two sets of neighbours separately. We can't add the neighbours together as we did in the previous example because they're not equivalent, so the number of lines in the signal from the central CH2s will not be 6. The couplings of the central CH2 protons to both sets of neighbours should be considered one at a time. Let's look at the splitting tree for 1-chloropropane. Every signal starts as a singlet, in other words one line, until split by its neighbours. The CH2 protons will be split by the neighbouring CH2 group into 3 lines. Each of these 3 lines will then be split into 4 by the CH3 group on the other side. This gives a total of 12 lines for this signal. Note that it doesn't matter which of the two splittings you consider first, you should get the same answer either way round. This is what the signal for this CH2 group will look like in the spectrum. The heights of the lines are according to Pascal's triangle. Here are some more practice questions. The answers are shown on the next 2 slides, so you might want to pause the screencast while you have a go. Thanks for watching, and look out for more resources coming soon on the Analytical Science Tutor channel.